Hello everyone, I'm Xingyu Chen, a PhD student from Nanjing University. In this talk, I will introduce our work, Retwork. It's a way to get the reader network with a commercial off-the-shelf RFID system. Here is the outline of this talk, including 4 parts: background, system design, evaluation, and conclusion. RFID plays an important role in IoT applications. A typical RFID system consists of 4 components: the computer, the reader, the antenna, and the tag. Since a tag is cheap and battery-free, it's a good choice for many applications in our daily lives, including our ID card and supply chain. As the scale of RFID systems increases, we need more readers to get a full coverage of the tags. In this work, we studied the way of getting the reader network in a multi-reader system. The reader network is a graph, where each node is a reader, and an edge between 2 readers exists, if and only if at least one tag is located at the overlapped zone covered by the 2 readers. In this example, V2 and V3 has an edge. However, V1 and V2 do not. The reason is that there are no tags in the overlapped zone covered by these 2 readers. The information of the reader network is useful. It underlies many multi-reader protocols. Besides, the reader network can be used to resolve reader clean. The reader clean problem happens when 2 neighbor readers run simultaneously. Their signals will collide with each other, such that the tags within the overlapped zone cannot be read. If we have the information of the reader network, we can know whether any 2 readers are neighbor or not. If they are not allowed to work in parallel. In this paper, we propose a time-efficient solution to get the reader network. Besides, to be practical, the proposed system must be Generation 2 compatible and can work directly in commercial RFID systems. Generation 2 is the widely used RFID standard. To get the reader network, a basic solution is tag inventory. All readers run in sequence to collect tag IDs. After that, each reader knows which tags are under its coverage. By comparing the tag sets, we can know whether 2 readers collide. If 2 readers have a same tag subset, they are neighbors. This solution works, but is time-consuming. The reason is that the readers need to query all tags, one at a time. In a large RFID system, the number of tags is usually big. It takes quite a long time to query all tags. To improve the time efficiency, we propose Retwork. It has 2 phases. The first phase is over-the-air writing. Specifically, each reader broadcasts a unique index to all tags under its coverage. After getting the index, the tag will store it in its memory. The second phase is selective reading. In this example, the reader VI checks tags with index J. If it detects any tags in the field of view, VI and VJ are neighbors. In this case, Retwork uses one tag reply to detect a contention link. In contrast, tag inventory uses 6 in this case. So Retwork is more time efficient than tag inventory. The above solution is quite simple. However, in the first phase, the reader needs to write a group of tags by one command. This one-to-many write is out of the scope of generation 2. So the way to implement the one-to-many write is the key to improve the time efficiency. Now, we introduce how to implement this process in practice. Generation 2 is the widely used RFID standard. It defines the physical and logical interfaces between readers and tags. We use 3 related functions in Generation 2 protocol. The first is the inventory flag. The second is the select command. The third is the query command. Now, I introduce the first one, inventory flag. As mentioned before, one-to-many write is not allowed by Generation 2. However, we found that the inventory flag can be changed by only one reader command. Specifically, a reader can set all tags under its coverage to the state A or B with one command. If we can piggyback some useful information in a reader's command, such that all tags memories are updated in the meanwhile, then we can mimic one-to-many write. The second function is the select command. It allows a reader to choose a subset of tags to reply. It can also set inventory flags to state A or B with a bit mask. The select command has 6 fields. The first is target. It indicates which flag to be used. A tag has 4 inventory flags. In this example, target is equal to 1. So the first inventory flag is used. The second field is action. It shows how can we set the inventory flag. The last 4 fields determine which tags are matching. If the string stored in the text memory is the same as the bit mask, then the tag is matched. In this example, the read tags are matching due to the bit mask 10. Their flags are set to B, while others are set to A. The third function is the query command. By using this command, we can let tags with state A or B reply to the reader. Query command has 3 fields. The field station means which inventory flag to be used. The field target determines which tags will respond, where 0 means the state A and 1 means the state B. In this example, all tags with flag B will reply to the reader. With the above functions, we next detail how to detect the contention link between any 2 readers. Considering a reader VI, we want to detect its contention link with VJ. The reader VI first sets its tags to the state A. After that, the reader VJ sets its tags to the state B. In the third step, the reader VI queries tags with flag B. If some tags with flag B exist, it means that the tags in VI's read zone can also be set by the reader VJ. So VI and VJ are neighbors for sure. Otherwise, if we don't find any tags with the flag B, VI and VJ are not neighbors. In this way, we can check each pair of readers, and finally, we get the reader network. Now, I will introduce how can we implement above functions with 3 Generation 2 compatible commands. The first command is for the reader VI to set its tags to the state A. In this select command, we use the second inventory flag. So the target field is set to 2. The action field is 0. It means if a tag matches the bit mask, its flag will be set to A. Otherwise, its flag will be set to B. The last 4 fields form the bit mask. 1000 means that all tags are matching tag. So this command is to set all tags inventory flags to A. Similarly, for the reader Vj, it needs to set its tags to the state B. The select command is similar to VS. The only difference is the action field, which is set to 4. It means that the matching tags are set to B, and other tags are set to A. The last command is a query command. It's used for the reader VI to check whether there are tags with flag B. The target field is equal to 1. It means that the tags with flag B would reply. With this command, all tags with flag B will reply to VI. By using these 3 commands, we can check whether VI and VJ are neighbors. For each VI and VJ, we run these commands. After that, we can get the whole reader network. We can further improve the efficiency through detecting multiple contention links together. First, all readers except VI set flags to A. After that, the reader VI updates the flag to B. Finally, each reader in turn queries the tags with the flag equal to B. If any reader conflicts with VI, then the tags in the overlapped zone must be set to B in the second step, and this reader can obtain the reply from the tags. Otherwise, no tags in the field of view reply. In this way, we can reduce the number of commands from 3 by m to 2 by m when detecting the contention links between VI and other readers. Retwork can also be used to detect redundant readers in an efficient way. A reader is redundant if all tags in its reader zone are covered by other readers. In this example, the reader VI is redundant. To detect whether VI is redundant, we first let VI set all its tags to the state A. After that, other readers set their tags to the state B. As shown in this example, V1 sets the flags to B. V2 sets the flags to B. Vj sets the flags to B. Finally, the reader VI checks whether tags with flag A exist. If there are some, it means these tags are not covered by other readers. The reader VI is needed. If no tags with flag A exist, the reader is redundant. In this way, we can quickly figure out which readers are redundant. We set up a prototype of Retwork. This is the experimental settings. We test 6 reader models and 8 tag models from 3 RFID leading suppliers. They are SIMagic, Impinj, and Alien. We use a total of 8,000 passive tags in our experiments. As shown in the right figure, these tags are attached to 40 boxes. Each box contains about 200 tags. Up to 8 readers are deployed to cover a desired area of 12 meters by 8 meters. Among these models, Retwork functions well on 4 reader models from SIMagic and Alien, and work well on all tested tag models. We stress that for Impinj readers, They actually support the setting of inventory flags, but they do not expose this interface to users. In this experiment, we evaluate the time efficiency. Since there is no existing work that studies the reader network, we compare the execution time of Retwork with the basic tag inventory. There are three scenarios: sparse, moderate, and dense. Sparse means 4 readers, moderate means 6 readers, and dense means 8 readers. Clearly, Retwork is more time efficient than tag inventory. For example, in the moderate case with 5,000 tags, the execution time is reduced from 55.9 seconds to 3.9 seconds. The performance gain is 14.7 times. This is a great performance boost. We also evaluate the accuracy of Retwork. We vary the number of readers from 4 to 8. In each experiment, the ground truth is obtained by tag inventory. As we can see, Retwork achieves a high accuracy. The false positive ratio is less than 3.5%, and the false negative ratio is less than 0.3%, which are small for most applications. We can further reduce the error rate by running Retwork multiple times. In this experiment, we compare the time efficiency of Retwork for detecting the reader redundancy. Similarly, Retwork is much faster than tag inventory in the 3 cases. For example, in the case of 6 readers with 4,000 tags, Retwork reduces the execution time from 40.2 seconds to 4.1 seconds, which improves the time efficiency by an order of magnitude. Now, we conclude this talk. First, we propose an efficient solution called Retwork to get the reader network. Second, we use the inventory flag to mimic one-to-many write, which is supported by the Gen2 standard. Finally, we implement our system in a COTS RFID system. Experiments show that our system has a great performance. Thank you.